let's do the integral now. Okay, let's do omega cross r, that's v, cross, okay, the B field, which is going to have two components now. So it's going to be basically B and S on the surface, R and S over R cubed, right? 2 R hat cosine theta plus theta hat sine theta. Okay, now fortunately for us, okay, life is actually not so bad because omega is just omega z hat, okay? And so as a result of this, because cosine theta is going to be defined by z, if you actually do this, do these cross products all the way out, only one thing will end up basically contributing to this thing, right? So I'll just save you a lot of time and just tell you what the answer is. It's going to be just this guy, right? So we just multiply everything out otherwise. This guy will give me basically omega cross r will give me an omega r sine theta. So these two sine theta will double up and give me a sine squared theta. All right. Okay. So that's the. So I'll save you a lot of grief about that. So write down what the answer is right now. Okay. So if we write down the answer, it's going to be the integral of omega, okay, r bns over c. Okay, move the c back in again because I'm funny that way. Rns over r cubed, right? And of course it's sine squared theta and then dr. Okay, beautiful. This is almost done. Yeah, we're like, all right, almost there. All right. Okay, now why did I talk about this light cylinder? Well, it's going to show up right here, right? This is going to basically give me the number of lines which are going to basically feel this effect. All the other lines are not going to, we're not going to worry about because we can't integrate a path such that it goes out to infinity. All right. Okay, so we're going to do this integral now. All right, it's going to be basically from the neutron star surface all the way out to infinity. All right. Okay, so let's just do that. All right, and if we do that, what we are going to end up getting, all right, is that we're going to get a factor. Let's see if I get this right now. This could be 1 over r. Let's see if I get everything right. It's r squared 1 over r. Yep, that's right. Okay. Okay. So if you do all of the integrals and stuff like that, you should end up getting something like delta phi is going to be proportional to. It still feels there's a 2 missing, but I'm just going to leave this proportional to here and then let you figure it out. Okay, so there's going to be a b here on the surface, and then there's going to be r and s squared, all right? And there's going to be omega over c. Okay, let's see. And then the sine squared theta. Okay, now recall that sine theta is approximately theta, all right, for theta is much smaller than 1, all right? And so what we're going to use here is basically theta naught. So this is going to be approximately equal to theta naught. And so sine squared theta is going to be approximately theta naught squared. So this is going to be approximately equal to, so delta phi. Okay, let me just move this up a little bit so you guys can see. It's going to be approximately equal to bns rns squared omega over c. And theta naught squared. Okay, so let's recall what theta naught squared is. This guy is just basically the square of the square root of omega r and s over c squared. Okay, so this is going to be equal to our final answer that we've been laboring getting, bns over rns squared over c omega, let's plug this in, it's going to be omega rns over c. Alright, that was good. We feel accomplished. Alright, and so the final answer that we get, something simple, not too difficult. Yes, and everything works out. So BNS RNS cube omega squared, what we want, over c squared. Okay, that is perfect. All right, now let's plug in some numbers here. Okay, so E max. All right, so we're going to basically figure out what the energy, maximum energy is. The maximum energy, if I face on this potential drop, will be equal to basically Z E delta phi, right? The energy that a particle achieves, right, is equal to the charge of the particle times the potential drop. So energy of particle is equal to charge times potential drop. Okay, so let's just do this right now. What is this going to look like? Let me make sure I move it up a little bit so you guys can see. All right, this is going to be equal to basically Z E delta phi, which is equal to Z E BNS RNS cubed omega squared over c squared, right? Which, if you run out the numbers, is going to be 10 to the 21, okay, electron volts. This is good, okay. Let's write down the rest. ZB over 10 to the 14 gauss. I had to really push the B field up quite a bit. And then it's going to be omega over 1000 hertz, right? Which is, so this is officially the fastest spinning, most magnetized system that's ever been observed, right? This is typically not something that you will get unless you basically have a magnetized supernova, all right, that generates such a large field. It's not clear you even get this sort of stuff, right? So this is typical fields. This, well, okay. I'll write what I need to write next. Okay. So, right. So, pulsars look pretty good, right? On the basis of this potential estimate. Okay, so they look great, okay? But this is really optimistic. Okay, must also count for losses due to curvature radiation. My God, I can't spell curvature. Curvature radiation. And Compton scattering. Right? Basically, pulsars, by their nature, because the magnetic fields are so strong and so, I guess, small, okay, it's 10 kilometers, so basically a charged particle basically encountering such a field would experience curvature radiation, right? So basically the same thing that limits the maximum power of the LHC more or less. And also pulsars, because they typically are hot young system, they generate a lot of X-rays, and so these X-rays can scatter off these charged particles and basically slow them down or just break them up. Okay, so that's basic pulsars. Now, the other thing I should note is that strong field pulsars are slow rotators. So typically B of 10 to the 14 Gauss might have an omega of maybe 1 hertz. Okay? And fast-spinning pulsars are weakly magnetized. Omega is typically of maybe, I would say, could I do 1,000 hertz? Maybe I could do 1,000 hertz. Yeah. Yeah, some of these guys are pretty fast. Is that right? Yeah. Okay, well, okay, let's just say that. B is typically maybe 10 to the 8 Gauss or so, right? So this lowers it by 6 orders of magnitude compared to what my earlier estimate would have given me. Right, okay. Now, there is a good reason for this, and the good reason is that if you're rapidly rotating and you're highly magnetized, you tend to slow down rather quickly. Alright, and so the only way to have basically long-lived pulsars that spin rapidly is if they're weakly magnetized, namely they don't give up much rotational energy. Right, so the estimate that we gave for this really, really high energy pulsar might be a magnetized pulsar, a highly magnetized pulsar that is produced at the moment a star basically collapses, basically during a supernova explosion, right? Because typically, if you rotate at this rate with this magnetic field, your lifetime is literally a matter of weeks or so, all right? Okay, so that's what I want to say for about pulsars, all right? For all the other cases which we're going to study, for all other cases, all right, the acceleration is due to shock acceleration. All right. Okay. So it's helpful. Let's consider this now. So let's consider this. Okay. So let's go to shock acceleration next. Okay, so to basically understand shock acceleration, we have to understand a concept known as Fermi acceleration, right? And the easiest thing to do Fermi acceleration is something called second order Fermi acceleration. Why is it called second Fermi order acceleration? Stay tuned. Okay, so let's talk about Fermi acceleration. Okay. Now, suppose for a second I start out with a cloud. All right, because in astrophysics, the entire galaxy can be thought of, but basically a bunch of clouds. All right, not even stars sometimes. Okay, suppose I start out with a cloud. All right, now this cloud is moving. Suppose the cloud is moving. Okay, so let's draw a very simple physicist picture of it. So all clouds in physics land is round, or are round. Okay, and they move with some velocity v with respect to some background, and in this background, basically there's a bunch of cosmic rays. Look at that. Okay, cosmic rays. Right. Okay. Now we're going to suppose that V is much less than C, all right? And so we can basically use Newtonian-ish approximations, right? It's not exactly the same, but it's Newtonian-ish. Okay, so all right. Let's see how do I want to do this now. Yeah, right. Right. Okay. So let's suppose we go into the cloud frame, okay? So we go into the cloud frame. The energy of in the cloud frame of the cosmic ray. Let's see if we can see this. You can't see this. All right, so that's helpful. So energy of the cosmic ray in the cloud frame, that's the cloud, is equal to, okay, gamma of the cloud. Okay, I'll write C for now. I won't use cloud. All right, times the energy of the cosmic ray in the so-called lab frame. I'll leave it without indent so you know what it is. Minus, let's see, beta of the cloud. So the cloud's moving with some beta, this V over C. Okay. And what else I want to do here? Yeah, I want to write basically the momentum of the cosmic ray in the z direction. Cosmic ray. So let's say this is the z-axis. All right. Okay. Times c. Okay. I apologize for those of you who are thinking I was using c equals 1. C is not equal 1. All right. Where beta of c is equal to v over c. All right. It's really beta v of this cloud here. And gamma of c, you can probably guess, is just going to be 1 over square root 1 minus beta c squared. Okay. So that is that. All right. So, that is the energy of that cloud. Okay. Now, let us suppose that cosmic ray, so that cosmic ray is in the cloud frame and suffers an elastic collision. So suppose in the cloud frame, the cosmic ray suffers an elastic collision. Okay. All right. So what that means is that the cosmic ray has been going in with what's going on here? All right. So let's suppose that this cosmic ray is coming in with some angle theta. So let's just draw that picture again. See if you see it? Good. Okay, so now the cosmic ray comes in, some angle theta, and basically comes back out with some angle theta prime. Alright. Okay, so if it suffers an elastic collision in the cloud frame, alright, because the cloud is much more massive than cosmic ray, right? That means that EC prime of the cosmic ray is equal to EC of the cosmic ray. So this is the scattered cosmic ray, and this is the initial. All in the cloud's frame. Okay. Alright. So, let's boost this guy back into the rest frame. Or not rest frame, into lab frame. Alright, well that's simple enough. We just revert everything we just did. So what we did initially was that we did